Moin, moin from me too. We've a lot to cover, so we're going to be speaking quite fast, and we had to cut some funny things, so ask us about them later. That's Elias. He's a theater engineer. He usually builds machines that catapult people onto stages in seconds, and he doesn't like water. And yes, hi, this is Nico. He likes to read incident report on ship incidents, and he also does sea rescue in the central Mediterranean. We said we'd do a consulting talk. Who of you has started to build their own submarine? Who of you are still in the planning phase? Great. For the rest of us, so that we can start on the same basics, here are the basics of a submarine. What do we need? We need a pressure body. Round is ideal. Then we build a tower on top of it so that the water doesn't flow into it. We also don't want to have it raining into it, and we need the ballast tanks. Let's put it into the water. When we do that, it floats. Why does it do that? Archimedean principle. The submarine is heavier than the waters because Archimedes said that things float when they weigh less than the water that they move out. But we flood the ballast tanks so that they're full, and then we float downwards. How do we float up again? We take pressurized air. That allows us to press the water out of the ballast tanks. We get buoyancy, and we move upwards again. And that's a very important principle. We need redundancy. That allows us to reach the surface even if one of these pumps breaks. But that's not where redundancy stops. We need additional security and safety. In the case of our submarine, we have ballast weights that allow us to sink, but we can ditch them. So if we were to have a problem, then we can ditch them from the inside of the submarine. We suddenly get a lot lighter, and we move upwards quickly. These cells are useful for sinking and moving up, but they don't allow for fine adjustments, and that's why we add a trim tank, which we can fill with water or air, and it allows us to gradually change our weight. We could summarize this as static diving. We change our position in the water only by changing weight, but there's a huge problem here. Water has different densities at different depths. The second problem is that small changes in weight are enough to move us up or down very quickly. But this happens a large amount, but this happens very slowly. In practice, this leads to a pendulum movement. We can improve on that by moving to semi-static diving, where we also add thrusters to the sides of our U-boat, and that allows us to do more gradual adjustments. In addition to that, you can also dive dynamically, which is what the small submarines do initially. Like all other ships, we have a rudder, but we also have a diving plane. It's a similar principle to aeroplanes. We can change it. Water flows over it, and it allows us to dive down. So much for diving up and down. The big question with submarines is pressure. I told you that round is a good form for a pressure vessel. So let's look at simply the pressure vessel. We have a lot of water pressure pushing onto our vessel. It's easy to quantify. The surface, at the water surface, we have 1 atmosphere of air pressure, and for each 10 meters that we dive down, we gain an additional bar. So at a depth of 20 meters, 3 bars of pressure are pushing onto this vessel, but on the inside we still have 1 bar. So this hull has to compensate for this pressure differential of 2 bars. What does that mean in practice? 1 bar is pretty exactly 1 kilogram per square centimeter, which is about the size of your fingernail, or your thumbnail. So there's 2 kilograms pushing onto each square centimeter of our surface. But the rear end of the boat is very much not round. It's not a suitable pressure vessel. If we dive with that, we have pressure pushing onto it, but the shape can't really resist it. It would be due to collapse. We don't want that, and that's why we use a trick. We have the same pressure on the outside as we have on the inside. No, on the same pressure on the inside as we have on the outside, which allows us to build pretty arbitrary shapes, and it means that certain parts of the submarine can be pressureless because there's no need there's no pressure differential. You run into a problem at some point, though. It's that air isn't a suitable medium, because at some point the pressure becomes so large that you can't really create that kind of pressure anymore, and there's suddenly a very small pressure differential, and we'd have to float back to the surface quite quickly. Let's look at the example of the Trieste, which was built by Auguste Piccard, and it was the first submarine to reach the bottom of the Mariana Trench. The actual pressure vessel is only the little ball you see at the bottom. It's got walls that are about 13 centimeters thick, and 2 people were sitting inside. This sphere on itself would sink, but to allow it to sink and to swim, they needed the buoyancy vessel, which is the large tank you see above it. As I said, air is no longer suitable, so they found something else, gasoline. It's a liquid, it's hardly compressible, and it's lighter than water. In our example, they had 7 cubic meters of gasoline, and because they didn't have the funds, it was borrowed. They use iron to sink, which they eventually ditch on the seafloor, which allows them to float to the surface again. Where do you look when you have questions about submarines, about certification, and so on? As we're trying to do a consulting talk here, we can recommend this document from the American Bureau for Shipping, which is a classification society that certifies ships, and they documented the material, the windows, how to test things, and what a human needs per day, how much they eat and drink and fart. It's a great document. You can find it online. We highly recommend looking at it in case you have questions about your submarine.
So let's come back to our submarine, how it started. So we covered the basics, and now on to the practical part. In the year 2012, I had a little crisis, a midlife crisis. I wanted to do something useful, and submarine, of course, is the thing to do then. And in the beginning, how do I find a pressure vessel, and what do you do if you don't have any money, and how can you recycle waste? And so we went to a big online auction and looked for people who wanted to sell things like that. And in this case, it was a propane tank. And people have that in their garden if they are not connected to the gas network. And this is a picture where I picked it up. And so I didn't get into discussions. I really declared it as a submarine initially to deflect any questions about gas content possible. So, but also we needed pressure vessels for water and air, and this is my first configuration that I tried. And on the right and on the left you can see these compressed air bottles for compressed air, and these are 4 ballast tanks. And my idea was that we could put that on the inside of the submarine, and then we operate that manually from the inside, and after half a year it looked like this. And in the beginning I thought there would be gondolas for the propellers in the beginning, and there were some other people became more important, and my crisis was over, and the submarine was far away, and I occupied myself with other things until the year 2019, and it looked like that at the time, and I really dug it up again. At this time, we were a bit older, and I needed something more comfort, so I wanted to sit instead of lie down, and so the tanks maybe should be installed on the outside. These are the yellow things here, and just don't draw enough, but really build things. So I really started to do that, and I installed the tanks on the outside, and you can see here there's also cutouts for windows. And we talked about the aft section, and this is the raw construction phase you can see from the aft section, and this is the final assembly state, and you can see the hydraulics that have been installed, and in the middle there's a round piece. That's the end of the prop shaft where the engine, the motor will be installed that now then drives the propeller. And it looked like this from the inside, and the pictures become a lot cooler now, and Serena came in, and she's a professional photographer, and I really want to document it. And Serena, thank you very much. And all these pictures there that look like someone took them who knows what she's doing, that's what she did, really. And she took all those pictures. So what you can see here is all the piping and some cabling also, and there are compressed air lines and water lines, and then everything was finished, and then I removed everything again and labeled it and put it on pallets. And what you can see here on the right side is the aft section. It wasn't installed for a long time because it's much easier if you install the things, if you don't have to put it thread it all through this little opening in the pressure vessel. And this was the moment where I installed the aft section and went outside, and we really painted everything in this really nice orange turbo paint. And when all the paint residuals from the skin fell off, and then there were wonderful help by a friend who came by. He's an electric engineer, and really put him in the submarine for 2 days and handed him cables and food. And after 2 days, the light came on, and there was a computer, and then we could install Linux on our submarine. So now it's really quite comfortable inside, and the tools are there because it's really unnerving to hand the tools in and out. And so we really have a tool corner there, and it looked like this from the outside. And it's really an official submarine now. And now we could really go diving. Ooh, okay. But now let's take a step back, and we talk about some details now for your submarine. And one is the hatch at the top. Thank you very much. This is the drawing of the top hatch, and it's a two-part. It's the hatch itself, and then the counterpart, the part that sits on top of the submarine, where the gasket is, that makes it watertight. And we talked about forces and pressures. If you dive 15 meters, it's like as if your neighbor parks his new Cybertruck exactly on the hatch. That's about the forces that it has to withstand. And so it has to be quite precise, and the gaskets work well. Okay, now we really know about metalworking, and it is a welded construction. And if you weld metal, you have one problem: it becomes hot and recrystallizes, and then changes its shape a little bit. That's quite normal. Means after welding, you really have to machine it again so that it is plain. It's flat again. So how big can such a hatch be? In our case, this is the biggest thing that would fit on the lathe, maybe 1 millimeter perhaps, and I install it here, quite proud, for post work, and it's really very flat now, and with a ridge in it, and an O-ring will go there, and it's of course a stainless steel because it shouldn't rust in the water. Now the thing is done and can be installed on the submarine. We put it on the submarine and welded it in place. Of course, what else? And you can see after that it was really crooked again, so the submarine didn't fit on the lathe to work it again. So we made this construction here, and it's really a hub of a VW Golf, and the hub is really in the middle, so we can really had to remove 0.4 of a millimeter, and after that it was perfectly level again. With the hatch it was easier because it didn't have to be welded, and we could just work on that on the lathe. So the next point, now we want to go diving, of course. And so where would you do that? And there are two possibilities. You go to a lake, and you have lots of publicity, and they would really have a lot of schadenfreude and know everything better than you. So maybe we need some lab conditions, so we really need a pool, really. And that's really complicated. There are two ways to make a pool. You can dig a big hole, or you build it up upwards, like a little garden pool. And we chose the second option, and we built up a pool. And we really looked where to get material, and we knew how to work with steel. And someone really gave us some steel, and we built the pool from that. And the next problem is how to get the submarine into the pool. So we didn't have a crane who could do that. So the simplest thing is we just built the pool around the submarine. And then we don't need a crane. But of course it's like this now. There's the base plate, and we welded it in place, and then put the submarine inside, and then built up the pool. And so you see what kind of lifting device we had for that. And the pool is 6 meters in diameter and 4 meters deep. And how much water? It's about 115 cubic meters, so 115,000 liters. It's quite a lot of water. A little pool. The water in the pool gets strange and have algae and dirt, and so you really have to filter it. And we really had to find something that's cheap, and we had some filtration device cheap, and there was an electric engineer we still had, and could you please connect it up for us? And he did that. And of course so that was also clarified, and we really could put water into the pool. And you can see that from the top here, and it took 3 days to fill it up. And it's like we were worried, and so the submarine is watertight, and is the pool watertight? That was our we didn't really know, but it was all tight, and after 3 days it really looked like this. So And now we really started making a few tests above water, really go forwards and backwards. And what is our first diving? What should it look like? And we really made some risk assessment. What could go wrong and what can we do against that? And all the people were briefed what to do on that day. And then it was really, we really could close the hatch the first time and really start diving, and really had some scenario what happens if the submarine dives and turns and lies on top of the hatch and we can't get out, and really so all the problems that could happen. Diving down, and it wasn't sitting on the hatch, so it was as planned. And of course, after diving, what comes after that? So what is different to a ship? It can also float up again. So we made this little video, and yeah. So you can, in conclusion, we can say do that with a pool. It was a really good idea. So find a place where you can test that in quietly. And so you can get help if something goes wrong, and you have a good plan. So let's just go on. We talked about emergency procedures. There's no air, and we need to get rid of the ballast. So what happens in the worst possible case? And what was clear is there may be a moment that we don't want to experience, that we might get off the submarine underwater. How can you train that? Maybe in the raw construction, but the hatch was the last thing to install, so it wasn't really a good way to fill the submarine up with water. But now we had this pool, and we really we could do a pool party. And if we do a pool party, of course, then we need an underwater phone booth, of course, with a bar, of course. And we had a wonderful party, and it was really great. And you could really phone home with the landline. And so we found that it's all perfect. We install the original hatch onto the hatch, and so we can simulate emergency exit. So there's the hatch on top, and really use the same safety, security equipment. We had two scuba diving bottles, and did some briefing and invited many people to help. And we tried then what happens if the submarine fills up. So we really have to equalize pressures, and then you can open the hatch and exit. And there's of course the moment where you really have a strange feeling and the water rises and you can't really escape because there's the ceiling. And so how can we really create more stress? We were much too calm, and it really wasn't an emergency, so we don't really need, we use only one compressed air bottle and really have to swap that back and forth. And it was a little more intensive, and if it's really, the water goes above your nose and you really have no air, but we really did that, and we really felt prepared. And of course the test really needs a logo and patches.
All right, next question that is always brought up. When you build a new boat, are you bringing oxygen? The people that ask you this always assume that you only breathe in, but factually you also breathe out, and you breathe out CO2. CO2 is poisonous, and the CO2 that collects inside the submarine becomes poisonous much sooner before you run out of oxygen. So even at 0.5%, you're already getting issues. Beyond this, it becomes so toxic you might die. So the question is, how do we get rid of the CO2 inside the submarine? So for this, you can use special calcium powder called breathing calcium that reacts with the CO2 in the air and removes it out of the air. So here you see the data sheet and the formula for all the chemicals. Another side product of this process is water. So where do you need this? In special medical devices or in rebreathers. When going scuba divers, it's also used in spaceships and submarine. Well, now the question is how much can it absorb? So 1 kilogram of this can actually filter 100 liters of CO2. So we built a special pot that we filled with the calcium. We were able to fill 4 kilograms in there. And then we calculate how much CO2 a human produces. And it's about 1 liter of CO2 per person per minute. So this canister allowed us to absorb 200 minutes of breathing, for 2 people. If you need more, you just build another pot, or alternatively, you could just bring additional calcium absorption material to refill it. The special material also has another special property that it changes color when it absorbs CO2. So that's very useful when you want to check if it's working and how saturated it is. So that's very practical. So now that you know about just the existence of the granulate is not enough. Of course, you also need to circulate the air. So we tried, actual fans are not enough for this purpose, however. So, for example, like you have on your GPU, you really need radial fans that produce larger amount of pressure. They're much more useful for this application. So if you plan to build something like this, make sure you use radial fans. And the pressure is much higher. All right, perfect. We built this. So now it's time to test. We tested it by just getting bottled CO2 and injecting it into this chamber. And we also got a warning device for gas, a warning device that's used, for example, in mines or by firefighters. So in this case, we really care about the CO2 and the oxygen in the air. So now we have a device, we can monitor the gas, and it works. So we just have this in orange. Of course, it exists in other colors from other companies. So quickly, to continue with the oxygen, to the initial question, yes, of course, we bring oxygen. Here you see one of our oxygen bottles inside the submarine. So here also with some napkin math, it's very similar, 1 liter of oxygen per person per minute. So we brought 2 bottles, which gives us oxygen for 16 hours. What can you learn from this? Test your system, do calculations, test your system, stay calm. If you stay calm, the air will last much longer. All right, the first test in the pool was successful. Of course, it's clear we want to get out of the pool, we want to get into the lake. Now, the problem is, how do we transport the submarine to the lake? We, of course, can't build a lake around the submarine this time. So we need a transportation cart. So we just quickly built one at night. It was kind of a hock work. But we were a bit worried that the submarine is very heavy and we have to push it over very soft ground. So we're very, very worried that it will sink into the soft ground. So we decided to take 2 wheels on each side to make sure that the surface of the special wheels is properly distributed onto the ground. So normally you push this into a lake with a car or a truck. The problem is that the area we wanted to put the submarine into the lake was very shallow. So as you can see, the submarine is about 2 meters high and in a shallow area we have to push it in rather far. Luckily, we met Valdi, and he drives an amphibious car called Amphi, and it's a former US Army Second World War device. It's not an issue, it can just drive into the lake. It has another problem, though. After about 1 meter of water height, the car starts to swim, so we no longer have any way of propelling ourselves forward on the ground. So we built a special push rod to push the submarine into the lake. And as you can see, it worked. We were on the lake in the water. All right. Are you ready for the first dive? All right, not yet. We have to quickly discuss one more thing. We wanted to have a communication device so we could communicate with the people on the surface. We didn't want to use a cable because you could get stuck or it could rip off. We wanted it to be wireless. So the other problem is that radio frequencies don't really work underwater. They're just absorbed by the water and they don't travel well. But what works really well, that we know from Wales, is actual sound. Water is not compressible, so the audio waves travel really well through the water. So what can we do to send the audio waves through the water? We were able to find these antennas. A lot of these were piezo antennas that would vibrate the water. It uses a special ceramic that if put under current, it changes its shape. So you know it also works the other way around. If you bend it, it also returns electricity. It uses a special piezo membrane and allows us to work both ways. You also can find it in lighters. When you press a button on an electric lighter, this actually produces a current and ignites the flame. So what you see here now, these are so-called echolode sensors or actuators. They're originally used in boats to estimate the depth. They send out a special sound wave and wait for it to return, and based on the travel speed of the sound, you can determine how far the ground is away. The second thing you see is an ultrasound speaker from an ultrasound cleaning device. So it's the third. So all of them have one thing in common: they only send in one direction. Of course, this is by design, because an echolode is supposed to measure downwards. It doesn't really want to measure to the side, so it's quite directional. So we did a bit of research, and you can also buy these in the form of a pipe, which, as you can see here in our drawings, send out the audio waves left and right. So we took that as a compromise and decided for this antenna. It gets a bit more complicated now. How do we even get a useful signal out of this? Here, if you use a constant current, constant AC current, we did an analysis of how big the frequency response is based on this. So you just have to keep one thing in mind. So there's a current limit. If you increase the gain too much, eventually you will destroy the speaker. So we were looking what is a good space in which to operate and in which to have the best gain, or essentially get out the most power. We were able to determine these 3 peaks, which operate at the resonance frequency of the sensor, so they're more efficient. So it's about, we are checking 300 Hertz to 3 kilohertz, and that's also what you need so you can actually be understood. The problem, of course, these peaks are very small, and it turned out that the bandwidth we need to actually submit voice was way too wide to really fit into these peaks. So for a cleaning system or an echolode, it's it's totally fine because it only really operates on one frequencies, and you can just pick the one that's optimal. So we had to do some more research. Here you can see actually we used a special bathtub in which we measured the overall transmission power. We also didn't realize right away that the tub was producing a lot of reflections, so it turned out we ended up measuring a bunch of noise, and we got kind of stuck. So we were looking a bit further, and we were able, as another option, we then purchased a broken underwater transmission system, and we started reverse engineering it, and we realized that they were actually using a different property, and they used a very flat area where they could transfer the sound much more efficiently and without distortion. So now the next thing we had to look is how sound travels underwater and what kind of noise sounds are there. So here you see a graph of the sounds of traveling ships and also rain and other sounds you can hear underwater. So we use this to make sure to transmit our audio in an area where it's very quiet, so that we would not get too much noise from any other noisy things on the lake. So we realized we had to push up the frequency a bit. We had to consider that we found an area where it's quiet. We had a certain area in which our antenna could operate, so we had to kind of shift the frequency and where both of them were optimal enough to work. So here's a bit of an example. Here you can see we did this calculation for various frequencies that would be found in regular voice, and you can see there's a carrier frequency and the actual frequency that then was used to transmit the audio. So as you can see at 300 Hertz, the lower part of the voice spectrum up to 3 kilohertz, you would get these special frequencies, and on the receiving side we then just do the opposite and subtract the carrier frequency again, and that way we can make sure that the voice is not switched and pitched in any way. Just remember, the actual signal is shifted by the carrier signal, and the overall frequency varies by the shift, and the received signal is then increased in loudness equally to the shift. So in this time we tested a lot, we hacked a lot of things together and tested. You can see here we're doing a lot with batteries from electric drills. You can see people would come by and ask us if we were talking to the fish, and we would send somebody else with a boat to check how far the sound would travel, and we finally able, after a bunch of tests, to have 2 kilometers of range. We were then excited to put all of it in a device and get it going.
What can we learn from this? It's definitely more complex than building a submarine. It wasn't nor was it cheaper than buying a functioning commercial system. But we now have a lot of measuring technology that can be used for other silly things, and we put all the circuit diagrams online, so you too can build one of these. Can we dive? No, we're in Germany. There's one more thing to deal with, and that's bureaucracy. The thing is, every boat on internal waters needs to have a kind of license plate. We want to register a motorboat. So what's the most reasonable thing? Of course, we want to go to the German Automobile Club. They said, nah, not a problem, send us some photos. We sent them some photos, and they were like, nah.
And we were like, why not? And they said, this isn't really a boat in the classic sense and more of a U-boat. And we were just about to discuss with them and trying to tell them that this was very much a sporting boat, a sporting vessel. But we got the tip that we were supposed to go to the German Sailing Association and say that we wanted to register our sporting diving vessel. And that's what we did. We sent photos from our dives in the pool, and then nothing happened for 14 days, and then we got it registered. We got the registration documents. So that's a tip for you. If you want to register a U-boat, register it with the German Sailing Association. And that's how we got the lovely registration 170 and so on. We slipped it into the water. We got insurance. We prepared everything, a boating crew, reinforcements. We were ready, but we did, however, not expect the water police to show up. Just as we were ready to dive, they came along and said, "Hi, can we do a check?" So we went back. We met them. You should always remain friendly. That really helps. We gave them our papers. The entire stack of documents we had. The data sheet for the biohydraulics. They looked at the U-boat and were slightly confused. They called the head office, who told them to take their pills. They were very confused. Is it a U-boat? Are you allowed to use it? We used the confusion because it turns out there is in the shipping regulation of Saxony there is a section that prohibits using submersibles. We thought either we try to ask for permission or we live with the consequences. They did some research, tried to understand what we were doing, if there were any other U-boats that had shown up in Saxony. But the case was eventually dropped. They referred us to another authority in Saxony. We asked us if this happens to you. We went for a dive. And finally, a video from the U-boat.
We're on the ground and we wait here for some minutes on the ground, and then we proceed further up, but we let you know. Over. At the moment we are on the ground. Over.
Okay, then bring away your next call. Hello.
So, jetzt? Oh. Das ist ja nicht deren Ernst.
Wassertiefe.
11 meters water depth. 8 degrees. 8.4 degrees water temperature. 1.5 meters to the seafloor.
Genau, also so haben wir am Ende auf ungefähr 11 Metern
That's
Tiefe
how we
Kuchen gegessen.
at cake at a depth of about 11 meters.
Okay.
What else is there to say? We slept for a day after all of this. Then we removed the boat from the water, looked at everything, and then we noticed this. These are the window panes, and there are these cracks in there, and that's really not great for a U-boat. We were preparing a talk for this congress, so we thought we needed a scientific approach, and we built this testing rig where we placed the window panes and did some pressure tests. tested some cycles. We were placing this at a depth of 100 meters, did that thousands of times, and did it with several materials. Polycarbonate, which is used in police vehicles, and acrylic plexiglass that you know. And with both materials, we couldn't figure out where these tears came from. And we got someone who usually builds aeroplanes to do some calculations for us, and he said that these should be okay for a depth of at least 200 meters. We thought maybe we apply too much torque here on these screws, on these bolts, and we tried to reconstruct it, do everything wrong that could possibly be done wrong, in the hopes of showing you a nice picture of one of these panes breaking. So we said, well, we need to get one of these panes to break to create a nice video for you. So we applied some real pressure from a pressure bottle and have this nice video for you. Unfortunately, you don't see the pane breaking, you only see the pressure chamber breaking. Suddenly water starts spouting from everywhere, so the pane would have survived even 450 meters of water. If there's someone here who is good with plastics, please help us figure out where these cracks come from and figure out what we should test next. What do we learn from this? Don't just trust the maths. There are these nice pretty pictures where green means good, red means bad. You have to test all the systems for pressure in reality. That's valid for the boat itself as well. So you have to submerge it without people on a rope to test your calculations, because it would be unfortunate if those turned out to be wrong. Serena, who took the pictures, won a prize, and at some point a friend sent me this picture from Tiflis in Georgia, where I was apparently hanging under a bridge. Besides Serena, we also got help from Christoph, who made a film about the construction of this boat and about us, and he managed to put the trailer online today, and it will be in cinemas at some point. We have a blog where we documented the building of the submarine and the circuit diagrams. If you have a lake or an offshore supply vessel that needs a submarine, please drop us a line. That was our talk. Thank you very much.
Thank you, Nico and Elias. Ich habe gehört, dass ihr unten in Halle H später auch noch Q&A haben wird, aber wir haben tatsächlich noch ein paar...
I heard that you're going to be in Hall H later, but we have some time for questions.
Ich habe als erstes Mikrofon 1
starting with microphone 1.
Two light-hearted questions. What kind of controller did you use to control? Are you doing this in carbon as well? Because that's a premium choice, I think. How did you power the U-boat?
Okay, I can start. The controls are not wireless, they are very much wired. It's a Harting connector and a self-built switch box, which have all the wires in there, so you can either like do it from the front seats or from outside, as you like, but it's very much wired. No carbon is, maybe we do some nice seats out of carbon, some nice seat rest. We will figure this out, but it turns out it's not the perfect submarine material.
Yeah, for the battery, it's battery powered, and we got a big battery box underneath, and it's quite heavy. And we use this battery box as well to do a trim, and we can shift it with a hydraulic cylinder backwards and forwards, and so we can adjust it. That could be right level. And this is the big orange box which is underneath the submarine. You can see it in Hall 8, and it's a forklift battery.
So, Microphone 3.
Microphone 3. Thank you for the great talk. A question about the tear in the plexiglass panes. Did you consider including the frequency from the motor?
No, we really didn't think about that. It's a bit strange because in the end we really were 15 or 20 meters and the calculations were a lot higher. We have the feeling that it has to be something different. Yeah, but it was just an idea. Yes, thank you very much. We really have to get to the bottom of that.
The internet has a question. It came up twice. How much did this cost you? Do you have an overview of that?
No, it's difficult to say. It's not really very expensive. If you really want to do it, just do it. It's doable. But we really have to clarify something. In the beginning, you need to find a suitable pressure vessel, and that's the only thing that you cannot change in the end. So be sure what it capabilities needs to have, or maybe you can have it built by a company, by a specialized company. It's not very expensive, so we could today build a better submarine, and that was one thing to start with.
Microphone 4. All inventors would be proud of you. You did a risk assessment. What's the most likely scenario in which you would die? And how much time do you have? Is it like a Hollywood movie where stuff starts popping up, or is it insta-kill?
So it really depends on the scenario. If the scenario is really you're stuck, you're hung up in a net, in a fishing net, or if you fall down into the Mariana Trench. So you can see it in the beginning, one of the pictures. One of the big weak points is the sail, really. So round shapes are great, and you may have seen that the sail is really really not round, as it's edgy. And as we found out in the calculations, it's one of the weak points. This would really fail first.
I have a question about the registration. Did you not have any documents? Was there no checks done afterward?
So it's the case with sport boats. So short answer is no. Nobody came to look at it. So you didn't register it in Germany? So yes, in Germany, sports boats, there's no requirement to have them tested or verified. If you have a small yacht, if you don't use it commercially, you just use it privately, there's no classification agency. You have to have a compass or anything, but nothing else. It's a private submarine. We don't really want to rent it out for money or have a commercial operation, and it's really not suitable for that. It's just a fun project, so such a classification is really not there. No.
Thank you for the talk. You were talking about redundancies. Why does the hatch and the sail why is that a simple O-ring?
Well, yes, that's a good question. No, really. So, oh, that's the fire alarm again, but the stream is unaffected. You can say that the sail or the hatch have the big advantage. It's the lower we get, the tighter it becomes because the force becomes much higher. And so maybe with 2 O-rings that would be better, but is that really a problem with safety? Is one of them critical O-ring but we have some procedures that we check the O-ring before closing it, and is the surface really flat and clean? So yeah, do 2 O-rings, sure, do that.
I wanted to ask if you thought about decompression sickness. At certain depths, you were probably expecting to go deeper than just eating cake at 11 meters.
So we really have inside the pressure vessel, there's a standard atmospheric pressure, so we really have no problem with the bends.
Didn't you say you would stabilize it by increasing the pressure on the inside?
So that's only the aft compartment, only the motor compartment, but the inside part is only under 1 atmosphere. But if we would do that, yes, then nitrogen saturation would be a problem. And we have a decompression table, and so we found out where the next decompression chamber is. It's in the university clinic.
On some pictures, you could
how we put in the stringers is really, we did a finite element simulation, and that includes all the stringers, and so we really put steel on it until the FEM showed that it was stable enough. So the entrance hatch is the biggest problem, and there are lots of triangles. In 2012, I really built it rectangular, and when we were stuck with that, and today I wouldn't do it like that, you can really show where it would fail. It's really this place on the top, and you can really see thousands of triangles, and it's really the desperate attempt to get it stable.
I have 3 questions at once. A short one to begin with. The pressure equalization in the engine compartment, is that done the same way in normal submarines?
Yeah, that's the principle of pressure compensation, and it's really commonplace. And there are other concepts as well. People who fill the motors completely with oil, and oil is incompressible, and so that's another possibility. But it's not all submarines do it, but it is one valid concept that you can do. And if you have lights on the outside, you would also pressure compensate those or fill them with something to make them incompressible, and it really makes your life easier.
Did you have, for deeper testing phases, did you have any ideas on how to do it unmanned?
Yeah, it would be nice if you have a lake that's not in Saxony, but of course that's a future project, yeah. So about
if you could remote control the pressure tanks, for example.
Yes, on the ballast tanks we really have connections for hoses, and you could put on a 100-meter hose connected to that, and that would be possible.
And thirdly, is there any reason why you chose single-side band?
Yes, the problem is with these transducers you can only transmit a certain power, and it's the modulation where you can use the entire power into the usable signal, and that's the reason really. But there's another one which we couldn't mention, and cavitation is really a problem with the transducer. If it contracts faster, then the water can go in, and a vacuum is created, and it distorts the transmission. So we really don't need to put the power into the carrier wave, but we really want all the power in the usable signal.
Nummer 1.
Already asked a question. There's somebody new there.
Oh, okay, sorry. Nummer 4.
Thank you. I wanted to know how you handle ditching, because this is your last option for security if all else fails. How you ditch the ballast so that nothing flows into the submarine?
I prepared something for you, and there's a key that's in a lock, and there's a shaft that goes through an opening, and this shaft really has 2 O-rings. It's really watertight. And really fast we go down to the submarine, and everyone who still has a question or wants a beer or a mate, come down with us and we can continue talking there. But we really thank you for our interest, and thank you very much to Nico and